What happens to trees as the climate warms? Hello friends, Jim here. Article published on the online publication phys.org. Trees struggle to breathe as climate warms, researchers find. And here's a photo of a bunch of trees. Trees are struggling to sequester CO2 in warmer, drier climates, meaning that they may no longer serve as a solution for offsetting humanity's carbon footprint as the planet continues to warm, according to new research done by Penn State scientists. We found that trees in warmer, drier climates are essentially coughing instead of breathing, said Max Lloyd, assistant research professor of geosciences at Penn State and the lead author. This was originally published in the Proceedings of the National Academy of Sciences. They are sending CO2 right back into the atmosphere, far more than trees in cooler, wetter conditions. Okay, we all know about photosynthesis, right? Plants, trees remove CO2 from the atmosphere, combine it with water to make glucose, other carbohydrates, and release oxygen. Yet under stressful conditions, trees release CO2 back to the atmosphere, a process called photorespiration. Now, this is a different process than transpiration, which is basically evaporation of water out the stomata of the leaves of plants. With an analysis of a global data set of tree tissue, the research team demonstrated that the rate of photorespiration is up to 2 times higher in warmer climates, especially when water is limited. Okay, what's going on here? The air is getting warmer. Warmer air can hold more moisture. It's doing what? It's sucking the moisture out of the ground, leaving drier conditions and, of course, the warmer conditions. So this is being fed upon by what's changing in the atmosphere. So the researchers found that the threshold for this response in subtropical climates begins to be crossed when average daytime temperatures exceed roughly 68 degrees Fahrenheit and worsens as temperatures rise further. The results complicate a widespread belief about the role of plants in helping to draw down or use carbon from the atmosphere, providing a new insight into how plants could adapt to climate change. And by the way, for 68 degrees is 20 Celsius. Importantly, the researchers noted that as the climate warms, the findings demonstrate that plants could be less able to draw CO2 out of the atmosphere and assimilate the carbon necessary to help the planet cool down, and assimilate the carbon necessary for the plant's own tissues. Let's add that in there. So once again, those people say, whoa, warmer planet, more CO2 is plant food. They really don't know what they are talking about. And they just need to close their mouths and zip it shut. We have knocked this essential cycle off balance. Lloyd said, plants and climate are inextricably linked. The biggest drawdown of CO2 from our atmosphere is photosynthesizing organisms. It's a big knob on the composition of the atmosphere, so that means small changes have a large impact. Plants currently absorb an estimated 25% of the CO2 emitted by human activities each year. But this percentage is likely to decrease in the future as the climate warms, especially if water is scarcer. There it is. And if the ground is drying up, the roots have less water to pull in to combine with the CO2 to make carbohydrates and oxygen as a byproduct. When we think about climate futures, we predict that CO2 will go up, which in theory is good for plants because those are the molecules they breathe in, but we've shown there'll be a trade-off that some prevailing models don't account for. The world will be getting warmer, which means plants will be less able to draw down that CO2. And don't forget, as I did in an earlier video, the stomata don't know what to do. Do they stay shut to prevent the water loss? Or do they open up and then pull in CO2? Well, there's a lot of them are staying shut to prevent the water loss, which means they're not drawing in the CO2. Well, now if you throw this in there, they're really not going to be drawing in CO2. The double whammy here. In the study, the researchers discovered that variation in the abundance of certain isotopes of a part of a wood called methoxyl groups serves as a tracer of photorespiration in trees. Okay? We all know what isotopes are. It's different varieties of an element. You have the same number of protons that identifies the element, but the number of neutrons vary, and that's what gives you different isotopes. So carbon-12 has 6 protons, 6 neutrons. Carbon-14 has 6 protons, same number of protons, but 8 neutrons, right? And then you just add the two together to get your isotope number. Okay? The number of protons identifies the element. So the team looked at the levels of the methoxyl variation of the isotope in wood samples from about 30 specimens of trees from various climates and conditions throughout the world, looking for trends in photorespiration. Specimens came from an archive at the University of California, Berkeley, that contains hundreds of wood samples collected in the 30s and 40s. So we're talking, basically 80, 90 years ago. The database was originally used to train foresters how to identify trees from different places around the world. So we repurposed it to essentially reconstruct these forests to see how well they were taking in CO2, Lloyd said. Until now, photorespiration rates could only be measured in real time using living plants or well-preserved dead specimens that retain structural carbohydrates. Structural carbohydrates like cellulose, lignin, okay, which meant that it was nearly impossible to study the rate at which plants draw carbon at scale or in the past. Now that the team has validated a way to observe photorespiration rate using wood, he said the method could offer researchers a tool for predicting how well trees might breathe in the future and how they fared in past climates. Okay, probably respire would be a better word here. Anyway, the amount of carbon dioxide in the atmosphere is rapidly rising. It's already greater than at any time in the last 3.6 million years, according to NOAA. But that period is relatively recent in geologic time. The team will now work to unearth photorespiration rates in their ancient past, up to tens of millions of years ago, using fossilized wood. The methods will allow researchers to explicitly test existing hypotheses regarding the changing influence of plant photorespiration on climate over geologic time. I'm a geologist. I work in the past, Lloyd said. So if we're interested in these big questions about how the cycle worked when the climate is very different than today, we can't use living plants. We may have to go back millions of years to better understand what our future might look like. You have heard me say often, if you want to get a handle on what's happening now or likely to happen in the future, look at the past. That's exactly what they're doing here. But I just want to mention this as well. They're using isotopes. Wally Broker pioneered the use of isotopes in various applications, including reconstructing past climate conditions. As we're seeing more and more scientists finding more and more different methods to utilize the concept of isotopes to facilitate and help in their analyses in what they do. So this is yet another application of the basic concept of using isotopes to help us understand what happened in the past. And this is all thanks to Wally Broker. So this overall, this is very troubling. If plants don't draw down as much CO2, then they're not going to photosynthesize as much, so the rate of photosynthesis will decrease, which means the tissues they add, their growth rates will decrease, and the rate of oxygen that they release to the atmosphere will decrease, which, by the way, we're already measuring a declining oxygen level in the atmosphere. So, more troubling news, folks. And as we cut down the Amazon, well, more troubles, right? The Amazon now becomes a carbon source, not a carbon sink. And what they're basically implying here is that trees could very well, if not at least be a carbon sink, may not perhaps be an outright carbon source. They might be carbon neutral, which overall means more CO2 in the atmosphere. So, we'll have to see how this proceeds along in the coming years. Thank you for your time.